Hello everybody and welcome back to Controlling the PBT playlist. In this video we will talk about peak control. But before going into details of this type of control, we will explain the difference between open loop and closed loop control. And we will also introduce the general PID control. Let's start. Let's imagine there's a heating plant of which we want to control the temperature in the outlet pipe. And through a valve we can act on the amount of fuel flow. There are different ways to achieve that. Here, for example, we report 3 different ways. The first way is a really experienced operator who knows by heart how to act on the valve to achieve a certain temperature. The second way is an operator who, using a temperature gauge on the outlet pipe, regulates the opening of the valve. The third way is leveraging some additional hardware, such as a controller, which, measuring the temperature of the outlet pipe through a transmitter and comparing it with the set point value, regulates the opening of the valve. The first 2 ways can be classified as manual, since there is an operator that has to act on the valve, while the third one is automatic. Another classification is based on the feedback. We can see that in the second and third case, the controller or operator commands are driven by the measurement of the outlet temperature and its comparison with the set point value. In the first case, instead, the operator doesn't have any information about the temperature of the outlet pipe, which means that there is no feedback. Of course, the second and third ways are more robust than the first one. In the first case, if something occurs in the outer pipe which makes the temperature drops, the operator will not be aware of that and will act as nothing has occurred, failing to reach the right outlet temperature. Instead, in the other 2 cases, the controller or the operator are aware that the temperature is decreasing, hence they will open more the valve to increase the fuel flow and make the temperature increase again until the set point value. When there's no feedback, we talk about open loop control. Instead, where there's feedback, we talk about closed loop control. In the third case, the loop is closed by the transmitter and the controller, while in the second case, the loop is closed by the temperature gauge and the operator, who acts as a controller. In our case, we want to achieve a robust control of the ball. Moreover, in a previous video, we have seen how difficult or even impossible it was to make the ball stay still into a certain location with open loop control. Hence, we will focus on closed loop control. In particular, we will start talking about automatic closed loop control. This block diagram represents the closed loop structure of our BBT system. The reference command is compared with the actual ball position measured by the touch sensor, and the error between these 2 quantities is fed into the controller, which produces a driving command for the servos. Our goal is to design a controller which allows the control of the ball respecting some performance requirements. To design our controller, we will make use of transfer functions. Hence, we will use the linear representation of the plant. The first thing we want to do is to define and compute the open loop transfer function of our system. Next, we want to define and compute the closed loop transfer function, which connects the reference position to the actual position of the ball. For sake of simplicity, we have computed the transfer functions only for the y direction. And also we will keep working with the y direction for the rest of the video and also for other videos. But what we do for the y direction can be seamlessly extended to the x direction. If we take a closer look to the expression of the closed loop transfer function, we can see that it is fully determined by the open loop transfer function. In particular, let's focus on the denominator, whose roots are the poles of the system. It is expressed as 1 plus the open loop transfer function. Hence, if we want to move the poles of our system to improve the performances, we have to act on the open loop transfer function. The open loop transfer function is given by the product between the plant transfer function and the controller one. we can't modify the hardware unless you want to buy another BBT system, so we can only act on the controller. And let's start to talk about controllers. The most common control algorithm in industry is the PID control. It consists on 3 actions: a proportional one, which accounts for the current errors, an integral one, which accounts for the past errors, and a derivative one, which accounts for the future errors. All classic linear controllers are based on combinations of these 3 terms on forward and feedback path. The PID control can be mathematically expressed in 2 forms: the academic one, where we can visualize the controller gain, the integral time constant, and the derivative time constant, and the parallel one, where the gains of the 3 actions are made explicit. Of course, we can easily switch from one form to the other with some basic algebraic calculations. Now, let's get familiar with the 3 different actions of the PID controller. Let's open Activate. In this model, we want to see the effect of each action of the PID controller, given a certain error as input. Hence, we use 3 different PID blocks, which implement the PID controller in the parallel form. In the first PID, we will have only the proportional action. In the second one, only the integral action. And in the third one, only the derivative action. As input error, we are given a combination of step signals. And let's run it. Looking at the scope, we can see that the proportional action will generate a command which is 2 times the error, since the proportional gain has been set to 2. The integral action will produce a command which is the integral of the error. Hence, the command has a shape similar to a ramp. Moreover, it's important to notice that even though the error goes to 0 at a certain instant of time, the integral action doesn't vanish. The derivative action produces 2 spikes where the error presents a sharp change. Everywhere else, where the error is constant, the derivative action disappears. This effect is called derivative kick, and it can be troublesome, in particular when there is high frequency noise. In order to reduce its effect, a filter is used in the derivative branch of the PID. In fact, if we look at the PID block, there is a 4th entry which represents the cutoff frequency of the filter. Reducing this frequency, the spikes will become smaller. The choice of the cutoff frequency depends on the system dynamic range. Typically, during the design of the PID controller, the effect of the filter is neglected. The effects of the 3 different actions in terms of performance metrics are summed up in this table, and we will get more familiar with that as we will design different types of controllers. Now we can move to design our first controller. Let's start with the simplest version of the PID control, which is the P control. In this controller, the only gain which is different from 0 is the proportional one. In general, this controller doesn't change the order of the system. It can reduce the steady-state error, but not eliminate it. And increasing too much its gain can cause high overshooting and eventually instability. We can insert it in our block diagram, and let's compute again the closed-loop transfer function. Before doing any calculation to get an optimal value for the proportional gain, let's try it on the real hardware, just setting it to an arbitrary value. We open Activate. In this model, we have implemented a proportional controller, and we set its gain to 5. As a reference, we give a 0 constant reference along the X direction and a step along the Y direction. Let's run it. We see that our controller doesn't seem that good performance-wise. The ball can't reach and stay still to the set Y position. It keeps oscillating, and indeed the oscillation keeps increasing with time. If we hadn't stopped the simulation, the ball would have fallen off the table. At this point, we can make 2 considerations. The first one regards the methodology. we do have a virtual model of the plant, for example the linear one. So why don't we use that to try to predict if what we have thought or designed could work or not on the real hardware? In this case, for example, also from the linear model, we could have figured out that the system was unstable and the ball would have fallen off. In fact, let's have a look at the system response running the linear model. We can see that, even if slower, its response is diverging. The second consideration instead regards this question. Could we have figured out before running any simulation that the system was unstable? Of course yes, and let's open Compose and let's compute the system poles. We see that there are two poles with positive real part. This means that the system is unstable. So the natural question is there any value for the proportional gain so that the system is stable? To answer it, let's run this compose scripts, which computes the poles and draw the root locus for increasing values of proportional gain from 0.01 to 22,000. If we look at the two complex conjugate poles, we see that their real part increases when the proportional gain increases. Moreover, we can see that even with the starting value of 0.01, these two poles have a positive real part. We can conclude that the peak controller is not suitable to control the BBT because it makes the system unstable. Hence, in the next video we are going to design another type of control, adding the derivative action. Lastly, let's have a look at the comparison between the real hardware and the BBT model. So let's set the status back to on for the real hardware and let's run it. We can see that the linear model of the plant provides results closer to the test data at the beginning when the rotations of the two servos are close to zero position and the linear approximation is more accurate. That's it for this video. If you would like to deepen your knowledge about system dynamics and controls, we encourage you to visit the first link. In this ebook you will find some of the topics we have covered in this video and many others. Moreover, feel free to share any questions you might have about Compose and Activate in the MBD forum. Thanks for watching and see you in the next video.